Okay, that this one is the last question in the second midterm, which was only correctly answered by a number of students only. And I think that indeed I wasn't expecting that much of a I was expecting a much better performance than that. And I tried to understand what was the problem with that question. And it's, from my perspective, I think for most of you, when you see the question like 100 dice are tossed by 100 different people at random times, so basically 100 say these are dices, although they look spherical, they are like these. So they are tossed, and we have 100 different answers: 1, 2, 1, 6, 2, 3, whatever. 100 different of those. Sorry, 100, and the average found to be 3.0. So the specific sequence is found, and the average of these values are found to be 3.0. You are asked whether the dices are fair. They, let's say, manufactured by a certain company, and these guys haven't made any tricks or something like that. So whether they are normal dices or not. So I think the problem why people were unable to solve this question, for most of the part they couldn't define the random variable clearly. I know I overemphasize, maybe you think that I overemphasize the concept of random variable and its definition, but I believe that's where the point is, because what they looked up is a kind of an event of 100 things going on together, and they wanted to define something out of this. And I think I haven't given any examples here, but for most of the people, once they write X is something related with the dice tossing, whatever they define the definition, then they say that X is normal distributed. And that's pretty much absurd, because we have only 6 values that can come out. So is it possible that it's normal distributed? But I think they're confused by the concept of these 100 things going on together. So let's be very clear, and that's why I wanted to give a step-by-step kind of solution procedure of this whole thing. So I think the way to go to solve these questions, like all the questions, to go from basics. Now, when I say X as a random variable, I try to search for an event which can come out with different outcomes, and these different outcomes are shown by a probability. Now, the atomic thing, the entity here, the smallest thing that statistical object I can define seems to be each dice. So this is going to be X is outcome of a dice. It's not specific dice, any dice here. It's not related anywhere with these 100 dices, and it's not anywhere related with 3.0. Take any dices of these representative dices, or dices out of which 100 representative ones are taken. You may take one of these or any other one similar to those. Outcome of a dice is equal to X. And in order to become X to be a random variable, indeed, it should take real values, right? That's what a random variable is. So it's going to be between 1 and 6. It's incorrect to write it that way. I should write it because it's going to take discrete values. So I should show it with this representation. And I can say that probability of X is equal to I here is equal to 1 over 6, where I is equal to 1 to 6. You can show it like this, or you can show it with a graphical representation where 1, 2, 3, 6, and it's going to be 1 over 6. And indeed, X is going to be uniform distributed, uniform discrete distributed, or this also is already means distribution. So this is where we should start the idea. Now, note what I did. I didn't bother with those 100 things, and I didn't bother about the actual value, which I'm always going to leave to the last, because this has got nothing to do with distribution. It is something to test the distribution. Now, from a theoretical, from a mathematical point of view, so I'm only in the mathematical realm here. It's not about physical thing. Maybe here, that's the point where I go physical, but still this is some idealization. Ideally, this is what I expect. So X is going to be uniform distributed, but X is the outcome of a single dice. So this is the first part A here. Now, let me, since this is a uniform distributed and this probability distribution, I can find the expected value here using either, if you like, X times Fx thing, but you don't need that in chapter 3, 4, I think it was in chapter 3, you can have the formulation where it's going to be A plus B over 2. So A and B here is going to be 1 and 6. So this is going to be 3.7, whereas variance of X is B minus A. I cannot remember exact formulation. Is it 1? Yeah. Plus 1 square minus 1. I should copy somewhere here. Over 12, I guess. So if you put the right numbers here, it's going to be 2.92, I guess. As you can see, this has got nothing to do with 3. This has got nothing to do with these 100 people. This is, I assume that this is the atomic entity of this statistical event. And it is this is how I define the random variable, and the expected value of variance of these random variable are those. Note that these are some idealistic concepts or some abstract concepts which has got nothing to do with actuality. So this is whole mathematical thing, but as I said, the only relation to physical reality is this part. But still, it's not an actual experiment yet. Let's continue to define another. Okay, now comes the description of the experiment. Still, I'm not interested in the result of the experiment, but from this atomic entity, I try to come up with an ensemble. And the example or the experiment is such that we have 100 of those independent. So see, these are different people, means they are going to be independent of each other. So it is A dice now becomes, we have another dice, we have another dice. If you like, you can give different random variables. So this variable name. So it's going to be the outcome of the first dice. Then Y is outcome of the second dice. And you can go to 100, but instead of giving all these different names or letters to each of these dices, I can do something more clever. I can write here Xi is equal to outcome of the ith dice, where I is going to be from 1 to 100. If I make such a definition, and definition here is in this fashion, if you like, we can get rid of X here, it doesn't matter. You can easily say A if you like. Let's give a different name, right? And each Xi, note that will have the same distribution as X. So each Xi here will have the uniform distribution with probability 1 over 6 and with the values 1, 2 to 6. Right? The random variable that from this atomic random variable, now this is that was the atomic one, as I said, but now we have all independent of these. So I should say AIs are independent. From these, I construct another one, and let me call it B. I'm on purpose using different letters that we haven't used so that you don't always shift. For instance, I can easily use X bar, but I don't want you to think. If I write X bar, you shift to your instead of thinking about the concept, you shift the memory about what X bar is. So I don't want you to think in terms of symbols, but in terms of concepts. Anyway, I define B to be equal to 100 of these toasts. So it's not, note that 100 times AI. Even at this point, if you write that, you can see that it doesn't make sense because A, which one? It is AIs added together. They are not the same thing. We do not multiply one tossing and then we do not realize one tossing and multiply it by 100. It's from 1 to 100. And let me, by the way, since I use I here and I here, it may cause confusion. Let me call this J. All right. So here the J, subscript J will denote the different tossing of the different coins, and whereas I is the different outcome. Anyway, B is equal to this one, and indeed it's not equal to this one because we are interested in the average. Therefore, we divide this value by the average. So this is what we call B. Note that we know very clearly how each A is distributed, right? Uniform distributed, independent from each other. Now the question is, we do not know the distribution of B. B is another random variable. Each I is a random variable. J is a random variable. This is a random variable. We know the distribution of each AJ, right? Very clearly, we do not know the distribution of B yet. That's what we have. So what we do here is we go from, instead of going from distribution to expected value, this time we just directly find the expected value of B. It's going to be expected value of this whole thing. And at this moment, we realize that indeed this quantity, just forget about this B part, indeed is equal to what we call sample averaging. So this is going to be, B is going to be equal to A bar, which we call X bar, which is sample averaging. So it's going to have all the properties that's related with A bar. And since this is indeed equal to expected value of A bar, since these are equal to each other, and we know from chapter 7 that expected value of E bar is equal to mu. And what does here mu represent? This is the expected value of the atomic random variable that we are interested in, which is this one, which is indeed equal to expected value of AJ. Which one, which of these J? It doesn't matter because they have all the identical distributions. They are independent and identical distributed. Indeed, they are IID, what we call. So expected value of B is indeed equal to expected value of AJ, which is equal to here, right? It's going to be 3.5, and this is equal to expected value of X. Note how I use different random variables, but they all mean the same thing, which is going to be equal to 3.5. And when it comes to variance of B, this is going to be variance of A bar, right? And this is going to be variance of what we call X bar here previously. So this is going to be variance of X divided by N, where N is the number of tossing of this coin, right? And this is again related with chapter 4. I'm sorry, 7. If you do not like this, actually, you should write, of course, write the given equation number. You can derive this formulation. How you are going to have this A1, A2, blah, 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 A100 over 100. And these are all independent. This is going to be 100 square. And these are going to be variance of AI summed together. And since these are independent, we are going to have 100. So these are going to be canceled. Therefore, it's going to be variance AI over 100. And variance AI is indeed equal to variance of X. Therefore, this is going to be equal to 2.92 divided by, where here and here, please, let's be very specific. It's not this value here. It is the number of times the dices are tossed. I'm sorry. 2.92 divided by 100. And now we have the variance. Now, what about the distribution of B? B is approximately normal distributed. Why? Because of the central limit theorem. Because central limit theorem says that, now let me write here, Z is equal to X bar. Here X bar is denoted by B minus expected B divided by variance of B here is going to be normal 0, 1. And B here is, if B is X bar, if n is sufficiently high. Well, this wasn't, of course, the form. I mean, the typical form is x expected value minus variance of x over n square root, or we have also the square root here. Actually, the reason why this was a little confusing is because I replaced x by b, right? A, b, all these different letters. But basically, that was the whole area. This is going to be normal with 0, 1 distributed if n is sufficiently high, which is n greater than 40. And here we have, let's use capital N. N is greater than 40. And instead of x bar, I have used b here. So x expected value of x is indeed expected value of b. And variance of b is equal to variance of x divided by n, which I've shown about. So this z is going to be normal distributed, which means this b is going to be normal distributed. That's what I'm trying to say. So you can easily say that this b is normal distributed with the expected value of b, which we have already found to be equal to 3.5. And this is indeed the average of 100 dices. And this variance is going to be 2.92 divided by 100. Therefore, if you convert it to, I think this is part, I don't know which part I solved. I think it's going to be C or something like this. Yeah. So the variable that I'm going to be defining is this Z variable that I'm going to be defining is our B value, let's say minus 3.5 divided by square root of 2.92 over 100 is normal distributed with 0 and 1. We expect that this is the case where B is average of any 100 observations. Note that up to this point, in no place I have still I haven't used this information, which is very important. I haven't still used anything related with that. It is still related only with the theory. Under some idealistic conditions with the experiments, with the definitions, I have just used mathematics, and this is what I come up with. Using central limit theorem, if you average any 100 diastolic experiments, this resulting statistic should be normal distributed. If, by the way, if so, can we always guarantee that? If this distribution is valid, of course, which means if outcome of dice n is from 1 to 6, if you have, for instance, a dice with 7 different faces, this is not going to fit. Why? Because the single dice, the atomic unit of that stochastic event will not satisfy the assumption here, where the assumption consists of a couple of things. What are those? This X should consist of 6 outcomes, and each outcome should be equally likely. Only under this assumption, this whole mathematical thing and the resulting this concept, this result will be satisfied. Now, if I conduct an experiment to see whether the dices I own satisfy this property, indeed, this is the reason of the experiment. This is why we conduct the experiment. Indeed, why we conduct the experiment is to check whether this assumption with 6 faces, okay, the 6 faces is obvious, it's going to have 6 faces, you can easily see that, but whether each of them are equally likely can be tested using this approach. Now, a more thorough analysis would be here. It will be indeed to check whether each of these faces from 1 to 6 have indeed 1 over 6 probability. And indeed, some of you try to do the test like 1 over 6 or not. Indeed, that would be a much more valid test, but unfortunately, that much information is not given to us, and it is what we call a multinomial distribution, which we haven't covered. Note that this could have been, if you had only 2 sides for a coin, then checking the coin for probability of 1 over 2 for heads or tails would be the valid approach. And for here, for whether each phase has a probability of 1/6 is the valid approach, but we don't have that much information. We are only given the mean value here. Therefore, we can still continue with whatever we are given to us. It's not going to be a wonderful test, but note that at the end of the test, you can only reject the null hypothesis that the dices are fair. Since you are not there to prove anything, you can either reject or not able to reject. So that's not a very a big loss that we are going to at the end. Therefore, with the information at hand, what we can most do is whether your mu is equal to 3.5. And what's mu? What does mu correspond to? Mu correspond to this atomic entity here. Each unit has a 3.5. And where does 3.5 come out? Because if you make these assumptions, mu comes out to be 3.5. Population mean should be equal to 3.5. So for 100, it's going to be 3.5, the average, the population mean. Or it's not equal to 3.5. This is the fairness or fair coin condition, I may say. Now note that this does not fully satisfy. It may be 3.5, but still the distribution may be like this. For instance, unequal asymmetric, but a distribution like this would also yield 3.5. I agree with that, but failing to reject null hypothesis does not guarantee that this is going to be 3.5. On the other hand, if you can show that mu is not equal to 3.5, you can guarantee that in a way that the coin is not fair. So therefore, this is the given information. This is the best test you can come up with. And in order to test this, this is going to be your test statistic. So now you write Z is equal to, now B is going to be, what was the definition of B? It is the average of 100 of these values. So this B is the average of these 100 of these coin tossing experiments. Therefore, for this specific case, I can say that B bar, which is the average of, now I use a lowercase value, is 3.0. So therefore, I replace this B, which is the theoretical value, with 3.0. And I expect this to be 3.5 and 2.92 over 100. And the value comes out to be, where is that? Minus 2.93. And we expect this value to be normal distributed. And to find how much we can tolerate, I think the test was at 0.01 significance level. We find 0.005, which is equal to 2.52. And you can see that this value exceeds this limit. Therefore, the coins are not fair. We do not know anything about the distribution because that's not that much information is given to us. But still, with the given information, the average value is far exceeds or lower than, much lower than we expect for this, for 100 of fair coins. This is what we have here.